Hello. Can you hear me? Okay. So this is a talk on hypothesis testing. I don't think in any of the workshops in Bhashini or before that we have had a talk on hypothesis testing as such. I think mainly because first of all, hypothesis testing is sort of taken care of in the sense that there are tools which give you a 95% confidence interval and uh, accuracy value, test of significance value, p value, etc., etc. So we do not really think about it and use the platform tools for hypothesis testing. But I thought that it is important to be, sensitized on these concepts of hypothesis testing, which are very important. The question is very simple. So in the evaluation workshop, we have heard many times some kind of blue figure, blue score being talked about, let's say for English to Assamese translation or Hindi to Konkani translation. And so these figures have been obtained from test corpus. Okay, and in particular, I think this has been done in the consortia, at least in Ishan and Vidyapati, on 1,000 sentences. Is that so, Rajanan? Is it 1,000 sentences? The test data is 1,000 sentences. 1,500 sentences. In-house also. Right. And there are a number of buckets. One is length bucket, okay, 0 to 10, then 11 to 20, and so on. And also domain bucket for agriculture, for administrative documents, for miscellaneous, etc., etc. Now the question is, if the English Marathi translation, Hindi Marathi translation, blue score is, let's say, 23 on this test corpus of 1,500. And based on this, we claim that the performance of Hindi Marathi machine translation will have 23 point blue score for the whole population. That means take any test corpus, okay, you will have this performance of 23 blue score, and that is the claim. Now, when we make this claim, see that it is based on these 1,500 sentences. Okay, so from 1,500 sentence to millions and millions of Hindi sentence translated to Marathi, will this blue score hold? That is the question. So from sample to population, what is the guarantee that the metric values will hold? So this question has been addressed by the statisticians in an extremely systematic way based on the theory of probability. Okay, and all this theory is very, very elegant, very powerful in their approach, and that is what we would like to look at. Even if it does not concern us directly, I think it makes us much more, wise with respect to all these evaluation and the claims that we make about them. So for hypothesis testing, so okay, maybe, yeah, thank you. So for hypothesis testing, the first and foremost tool of thought as well as framework formation conceptualization is probability and probability distribution. Okay, again, I apologize for preaching to the choir. I think all of you know probability and probability distribution, but there are always subtleties and traps because probability can surprise you. Okay, and I'll give you some examples, which is a very strong grip on probability and probability distribution is needed not only for hypothesis testing, but for the trade that we are in, natural language processing, AI, machine learning. So I give you a problem. This problem is the following. Whenever a mining is done, okay, we mine, then sand particles are produced, and we would like to estimate the percentage of sand grains in a pile of sand falling in a particular range. Okay, in the range X to Y, we would like to estimate that number, that percentage of sand grains. Now this is the picture. Okay, we have sand particles in this piles, and it is impractical to pick each and every sand particle, measure its size, and then document and then find out the percentage of sand particles which fall in a particular range. Impossible, right? You look at these piles and there are many such piles. So what is done? Okay, but before that, this mineral sand is an essential component of consumer products such as paint, plastics, and paper. So the sand that is produced by mining, it is not wasted. It is used for this kind of products like paint, plastics, and paper. And almost all titanium minerals are used as feedstock to produce titanium dioxide pigment used in products such as paints, paper, and plastic. So for the purpose of paints, for example, sand particles should be in the range of some size. Okay. So what we do is that, let's say we take a sample of 10 grains from a large pile, and they have these sizes. Okay, 2.2, 3.4, 1.6, etc., etc., and then 1.9. So we would like to estimate the percentage of sand grains in the entire pile whose size is between 2 and 3. Okay, so what is the immediate reaction? We would like to look at these numbers and see how many fall in the range 2 and 3. So if you do so, then the number of particles in the range 2 to 3 is 4. 2.2, 2.7, 2.8, 2.5. So out of 10 grains, 4 are in the range 2 to 3. Then we apply the ratio formula. So 4 by 10 is 40%. And from this 10, we would make a leap of generalization and say that whatever with the pile, from out of the whole pile, the percentage of sand particles falling in this range is 40%. So see the amount of generalization we are doing. 10 to the whole pile. Whole pile may have millions of sand particles. So now, is this correct? That is the question. So for that, we are a bit suspicious, and we go back to some science, and we go back to some interesting properties of the sand particles. So there is this interesting law due to Kolmogorov, a very eminent Russian mathematician. Kolmogorov's law of fragmentation. It says the size of particles resulting from the fragmentation of a mineral compound has a log normal distribution. Okay, so I'd like to draw your attention to this point. Whenever we have a situation with data, okay, data science, we would like to know what is the underlying distribution. So the size of particles resulting from the fragmentation of a mineral compound has log normal distribution. So a random variable x has a log normal distribution if log x is normal. Okay, so if you take y is equal to log x, then the probability density function of fy of y is fy equal to 1 by sigma root of 2 pi e to the power y minus mu square by 2 sigma square. So any normal distribution has a mean and a standard deviation. Okay, so this is a very important fact which I did not consider when I was taking the ratio of counts. I did not consider this. Okay, the fact that the particle sizes, the log of those sizes follow normal distribution. I did not use this. Okay, so do I gain anything from using this knowledge? Okay, so let's see. If we know the distribution, we must use it. So let's see how. This is the question. The percentage of sand particles in the range 2 to 3, and percentage is also probability. So our goal is to find out the probability of the particle size falling in the range 2 to 3, right? And this is equivalent to asking what is the probability that log x falls between log 2 and log 3. Okay. Then we use the machinery of probability. So what we do is that we have the sample size of 10 and the respective sizes of sand particles is 2.2, 3.4, 1.6, etc. up to 1.9. The log values are 0.79, 1.22, 0.47 going up to 0.64. Okay. So these numbers we know come from a normal distribution. These numbers come from a normal distribution. Okay. And we would like to make use of this fact. How do we make use of this fact? We were interested in the probability of log x falling between log 2 and log 3. I subtract the mean of these values, sample mean, subtract the sample mean, and divide by the standard deviation of these values, standard deviation of these values. So the mean is 0.75, standard deviation is 0.44. Then I find that log 2 gives rise to, after normalization, gives rise to minus 0.13, and log 3 after normalization gives rise to 0.8. Then we are asking what is the probability that this quantity log x minus 0.75 by 0.44, this is also called the z value. The standardized normal distribution is called is represented by the variable z. So what is the probability of z falling between 0.13 to 0.80? So this probability can be found from what is called the z table, and that probability comes out to 0.32. Now you see it is not 40% anymore. We are saying the percentage is 32%. It is less than 40%. Okay, and this value is likely to be much closer to reality because it is making use of the underlying distribution. So where is the error when we say the percentage would be 40%? Where is the error? The error is that the ratio of counts, when you take the ratio of counts, okay, this value, when we take this ratio of counts, the underlying assumption is that the underlying distribution is multinomial. Okay, the distribution is multinomial, whereas Kolmogorov's law tells me that the distribution is not multinomial. It is log normal, not even normal. It is log normal. You have to take the values, take their logarithm, and take and then apply the laws of normal distribution. Okay, that is the actual situation. So 40% cannot be correct. Okay, it is 32%. So what this is showing is that if you are able to get your hand at the underlying distribution, we have to make use of that. Okay, and if the distribution is not used, then anything we do is based on a wrong assumption about the underlying distribution. Therefore, the results also would be wrong. Okay, so this is a good example to show why probability is important and is giving us values which is principled. Now let's proceed. The second tool of hypothesis testing is the z-score based on z-test. So any normally distributed random variable x can be converted to standard normal form by subtracting the mean and dividing by the standard deviation. So that's something we have seen many times, also probably studied in school, college, etc. The normal distributions have mean and a standard deviation. You can convert any normally distributed random variable to its standard form. Then we have other important concepts. The area under any normal curve is equal to 1. Now when we have standard normal distribution, the mean is 0 and the standard deviation is 1. So here one thing we know is that we can compute the area from any point to any point between any two intervals. Okay, so the notation, this z value, and the probability of this z from minus infinity to up to z can be read from a chart. So area under the normal curve from A to B is the probability of z being in the interval A to B. Why the interval is important, I'll show you very soon with an example. Now, this probability of z lying in the range A to B is the area under the normal curve from z equal to A to z equal to B. Okay, this is a well-known concept. Okay, now the probability distribution for the standard normal form is this. So what is important is this z score table. So when you look at the z score table, maybe you cannot read it very clearly. We have these rows here starting from minus 3.4, minus 3.3, and so on. Two values here are important, minus 1.9 on the row and 0.06 on the column. So the way to read this is that you concatenate the column value with the row value. So you have minus 1.96 here, and the value here you can see in this cell is 0.025. Okay, what it means is that the area under the standard normal curve from minus infinity to minus 1.96 is 0.025. Okay. Similarly, when you go to the positive side, 1.9 and 6, the area under the curve is 0.975. Okay. So this area is 0.975. So from minus 1.96 to plus 1.96, the area is 0.975 minus 0.25, that is 0.95, 95%. Okay. So under a standard normal curve, from the value minus 1.96 to plus 1.96, the area under the curve is 95%, 0.95. So you will relate to this in the form of 95% confidence or 5% significance level. You must have seen this in machine learning papers. Okay, the meaning of 5% significance level corresponds to 95% area under the standard normal curve. Okay, so the way a z-score table is read is by concatenating the column with the row. Now this is shown here. Now let us take this idea to interval estimation. Okay, and I illustrate this with an NLP example, and we know that x bar is normally distributed with mean mu and known standard deviation sigma by root n. This is called the central limit theorem. This is the foundation again for hypothesis testing. It is called central limit theorem. The central limit theorem says that if I take samples from a population, assume that the population mean is mu, okay, and the standard deviation of that population is sigma. If the size of the sample is n, then sigma by root n is the standard deviation of the standard deviation of the sample, and if x bar is the mean, then x bar itself is normally distributed. So this is a very nice point. So let's say we have a population and we keep taking samples of size n. Okay, so let us take this. Let us relate this to our situation. We have a 1500 sentences corpus, test corpus. Okay, so on this I find the blue score to be 23. I have another 1500 sentences corpus. On this I find the blue score, let's say, to be 22, and so on. Okay, you might come back and say that these blue scores are not mean. The central limit theorem says that if you keep on taking samples, then the mean is normally distributed. Okay, that mean has a mean of that that normal distribution's mean is equal to population mean, and the standard deviation is the standard deviation of the population divided by root n. So if the blue score is not mean, then what you're talking about? So that's another small discussion. You have to use what is called an indicator variable. Okay, but let's proceed with this discussion. Okay, so the mean is normally distributed with population mean as the mean, and the population standard deviation divided by the square root of the sample size as the standard deviation. Then the sample mean also can be converted to a standard normal variable by subtracting the population mean and dividing it by the standard deviation, which is sigma by root n. How do I use it? I use it to estimate the population mean. From the sample mean, I can estimate the population mean. So this is something very, very remarkable. If the population mean is x bar, okay, then if the sample mean is x bar, population mean has to lie between x bar minus 1.96 into sigma by root n and x bar plus 1.96 into sigma by root n. It has to lie in this range with probability 0.95. Okay, so with 95% probability, 0.95 probability, the population mean has to lie between these two quantities. Okay, so how do I use it? I use it in the following way. I mentioned this in the on the first day. Suppose that a Hindi Konkani machine translation system called Bhattacharyya is made, and it is tested as follows. There are 9 test corpora, and the blue scores are 5, 8.5, 12, 15, 7, 9, 7.5, 6.5, and 10.5. Okay, these are the blue scores. And the company which has made Bhattacharyya is claiming something. Okay, it says that suppose it claims that I can ensure a blue score of 15. Will you believe it? If the maker says that I can assure a blue score of 10, can you believe it? These are the questions. Okay, so just look at the number. What does your gut feeling say? Will you accept the claim that the blue score will be 15 by looking at these numbers? Doesn't look like, right? And if the claim is the blue score is more like 10, you can trust this little more. Okay, so what is the basis of this? The basis of this is the interval estimate. So we have seen that the sample mean is 9. Standard deviation somehow we know is 4. So the standard variance is 4. So therefore standard deviation will be square root of variance, which is 2. The sample size is 9, so square root of the sample size is 3. Okay, so the population mean has to lie between 9 minus 1.96 into 2 by 3, 9 plus 1.96 into 2 by 3. That is, it has to be between 7.69 and 10.31. This is on the strength of the central limit theorem. Okay, so there is a 95% probability that the blue score will be between 7.69 and 10.31. Therefore, you will not believe the claim that the blue score is 15. Okay, and let the mean remain the same, and also the standard deviation is 2, but now n is 100. So this tells us why increasing the sample size increases our precision of estimation. So now if n is 100, we have this same expression here. Okay, x bar minus 1.96 sigma by root n, mu has to be between these two values, and 9 minus 1.96 into 2 by 10, 9 plus 1.96 into 2 by 10. Now the interval is 8.6 to 9.4. Earlier it was 7.69 to 10.31. Now it is 8.6 to 9.4. So the boundaries are closing in towards the mean value. Okay, this is a much tighter estimate of the interval, and with sample size we are going closer to the population mean. Now if the company says that I can guarantee a blue score of 10, you will not trust him so much. Okay, because the interval is 8.6 to 9.4. But with 9 as the sample size, you trust him. What does it show? It shows that as the sample size increases, our degree of belief also changes. Okay, so this is how sample size is related to to our belief. Okay. Now let me. I think I'm almost out of time. Let me introduce another important concept and then pass the floor to Nihar. Another illustration to introduce hypothesis testing. So we have a named entity identifier tagger, which is given a sequence of 50 words and is asked to identify if the words are name or no name. If the tagger tags 32 words correctly, what can you say about the accuracy of the system? So 32 out of 50 is 64%. Can you claim that the accuracy of the system is 64% anytime, anywhere over the whole population? So let's look at this problem a little more closely. This is the input. In the recent address to Congress, the US President Biden had Pelosi and Harris sitting behind him. In these, in the recent, etc., are non-names, so that's why they have this tag of 0. Congress is 1, US is 1, Biden is 1, Pelosi is 1, Harris is 1, because these are named entities. So, so I ask my question in a different way. I say, what is the guarantee that the underlying tool is doing nothing but tossing a coin and doing random guessing? Okay, well, because that is a baseline which you would like to investigate carefully. Okay, I have spent maybe $200 on a tool, and if the underlying algorithm is just tossing a coin and deciding on name or non-name, that is not worth the price I paid. So how do I check that it is not doing random guessing? This is done by what is called hypothesis testing, and I introduce some constructs of hypothesis testing. Let P be the probability of the tagger labeling the data correctly. There is a null hypothesis, H0. H0 is a notation given for null hypothesis that we want to demolish. The null hypothesis is that P is 50%. So the tagger that I have, its probability of being correct is 50%. That is, it is random guessing. So, and I also have to decide on the confidence interval that this has to be done a priori. 95% is my confidence interval. Now the process can start. So if P is the probability, then getting the correct tag. Is there some question or something online? Okay. So here again, some probabilistic concepts are useful. The probability of k successes out of n trials, we know from our knowledge of binomial distribution, is this expression: n choose k, p to the power k, 1 minus p to the power n minus k. So now this binomial distribution can be approximated by normal distribution if n into p and square root of np into 1 minus p both are more than 5. Okay, so this is something, let's say, we know from other sources. That's fine. Now we do this calculation. So sample mean is, suppose 100 words are given. Sample mean is 100 into 0.5, which is 50. Okay, 100 into 0.5 is 50, and square root of 100 into 0.5 into 0.5 is 5. So I can create a standard normal distribution variable x minus 50 by 5. 50 is the estimated population mean, and the standard deviation is 5. So my interval of estimation is minus 1.96 to plus 1.96. So when I plug in the value of z as minus 1.96, I get the value of x as 41. Plus 1.96, I get the value of x as 59. So then I am able to conclude the following: if the number of correct tags is between 41 and 59, given there are 100 words in the test corpus, I have every reason to believe, I have a very strong reason to believe that the named entity identifier is doing random guessing. Okay, see the conclusion. If the value is between 41 to 59 for 100 words, okay, for 100 words, then I have 95% confidence, okay, that the underlying tool is just doing random guessing. See the remarkable conclusion you are able to arrive at, okay. And where is the role of null hypothesis? The role of null hypothesis is this, that the population mean is 0.5. That means the probability of correct tagging is 0.5, which is no better than random guessing. You are able to estimate the population mean by this formula because of the null hypothesis. So the methodology is this: if the null hypothesis holds, that if it was doing random guessing, then this value of observation will force me to conclude that the tool is doing random guessing. Okay. Then there is this alternative hypothesis, null hypothesis, and so on. So let me just take one more small example. This also is very illustrative of hypothesis testing. A factory has a machine that the factory claims dispenses 80 ml of fluid in a bottle, and this needs to be tested. A sample of 40 bottles is taken. The average amount of fluid is 78 ml with standard deviation of 2.5. Verify the factory's claim. This you can always map to any NLP situation also. Okay. So you have a sample of 40 bottles. The amount of average amount of fluid is 78 ml with standard deviation of 2.5. This is my data. 40 is data. 78 ml is data. 2.5 standard deviation is data. All this is data. They cannot be refuted. This is right in front of my eye. Now I have the claim which is up in the air now. It dispenses 80 ml of fluid. Now, if the amount of fluid is more than 80, then the factory stands to lose money. If it is less than 80, then it amounts to cheating the customer. Okay, neither of which is agreeable. So we begin to address the problem in the following way. We examine the problem carefully, read the problem statement again and again, discuss the issues threadbare, and then arrive at H0. That is the starting point for any hypothesis testing. Or formulate the null hypothesis. Accordingly, formulate HA, the alternative hypothesis. It is the null hypothesis that we want to demolish. Okay. We decide also the confidence interval. This is another design parameter, and this automatically fixes the significance level 0.1, 0.05, 0.01. So 95% is most of the time used. It corresponds to the significance level of 0.05. Now let us see. This sets the rule of the game, and we cannot change it going forward. You cannot change the null hypothesis. You cannot change the confidence interval. Okay. So then from H0 and HA decide two-sided or one-sided test. Two-sided means the interval has to be from minus x minus alpha to plus alpha. One-sided will be minus infinity to something or something to plus infinity. Those are called one-sided. Okay. So in our case, for this test, let us see what is happening. So the claim population mean is 80. Every bottle has 80 ml of fluid. Sample size is 40. What we have observed is 78. Average is 78, and standard deviation is 2.5. If we are not coached in hypothesis testing, if we do not know the method of hypothesis testing, what will be your position? Since the average value is 78 is less than 80, will you say that I reject the claim? Will you say this? 40 samples, 40 bottles have been observed, and their mean liquid amount is 78. Claim is 80. 78 is less than 80. Standard deviation is 2.5. Will you reject the claim or accept the claim? What is your first reaction? Reject, because 78 is less than 80. So, so this is where I would like to draw your attention to little more principled approach. This question cannot be answered without first asking what is your confidence interval. With what confidence you want to reject or accept. This is the key point. With what confidence. My blue score is 23. Also give me the level of significance or confidence level. This part is sometimes not mentioned. What is the amount of test corpus you tested on? Okay. What was the diversity in the test corpus? Diversity is not handled here, of course, but the amount is important. So let's quickly see how this problem is solved. So for 95% confidence interval, I have to be between minus 1.96 and plus 1.96. If the value of Z falls in this region or in this region, below 1.96, minus 1.96 or plus 1.96, more than this, then we reject the null hypothesis. Okay, that is the methodology. So let's see. If ZC is plus minus 1.96, what is the observation? 78 is my sample average. Population mean is 80 as per the claim. This is claimed. Okay. So 78 minus 80 divided by 2.5, which is sample mean, and divided by square root of 40. 40 is the sample size. I get minus 5 approximately. Okay. All this is given to me. Now minus 5 falls in the rejection region. You see, minus 5 is here, far below minus 1.96. Then I'll reject the null hypothesis. What did the null hypothesis say? Null hypothesis says that the amount of fluid in the bottle is 80. Okay, amount of fluid in the bottle is 80. That was the hypothesis. Because of this, I could make use of the population mean. And since I am falling in the rejection region, I say that I reject the null hypothesis. Based on the data that I have, I cannot accept your claim that on an average, the bottle has 80 ml of fluid. Okay, you had also rejected without knowing hypothesis testing, well, 78 less than 80. But you know, if you change your confidence level, then you can get a case where the Z value falls within the region of confidence minus alpha to plus alpha, and then you cannot reject the hypothesis. Okay, and then people will come back and say that ultimately, what is your conclusion? Are you rejecting or accepting? And then I have to say that, you know, it depends on the confidence level that you have given. Then he says that just go to hell. I want to decide whether I'll do business with this company or not. Give me that. Okay. So that's why a lot of people sometimes hate the academicians. They think they're talking about useless things. Okay. But if you dig deeper, then there are underlying, you know, traps and subtleties which you can avoid by this kind of things. Okay, so I think I'll stop here. And what I have tried to communicate to you is that when you are giving all this performance figure, just do mention this confidence interval also. Okay, that's it. Okay, thank you. Nihar. So Nihar's topic is very important. Nihar is a PhD student in CSE department working with me, about to finish his PhD. He has been working in the area of bias, hallucination, and so on. He will talk about bias mitigation and detection in large language models.